not in class today, but I still wanted to make sure that I got to go through and explain. There's no assembly today. On how, sorry, I wanted to be the one to explain the keys so that I can explain specific things that I want you to look at and focus on, and then specific things I want you to see in the explanation as well. So the number one is to create a model to show how latitude affects temperature. The model that I chose was this one specifically because in my explanation, I have to explain why latitude affects temperature, and this model shows the why and not just the how. So I chose this model instead of the model where the equator is red, and then as you get farther away from the equator, the colors get cooler. I did this instead because it'll help me more in my explanation. So whenever you're drawing a model, you want to make sure that it's going to help you in your explanation, because in your explanation, you need to use your model. So if you just drew the map with the colors, and it would be a lot harder to explain in number two. So if you have a model that's like this one, but is maybe a little bit more detailed or whatever, that's good. This is the minimum that you would be able to do, okay? So in my explanation, this is what I say. The model above shows the Earth receiving light/heat from the sun. Because the Earth is a sphere, the center part, the equator, receive direct light, while the top and bottom, the poles, receive indirect light. So those first two sentences are just explaining what my model is showing. I specify that the equator is getting direct light and the poles are receiving indirect light because that's going to come back later in my explanation. So right here, I explain what direct light means. So direct light means that the light/heat is concentrated in one area, thus making it warmer. So here I'm explaining that the equator is warmer, and I'm also explaining why the equator is warmer. The equator is warmer because it is receiving direct light from the sun. Indirect light means that light/heat is spread out over a larger area, thus making it colder. Okay, so there I'm saying, I've said already that the poles are receiving indirect light. So in that sentence, I'm saying indirect light means that it's colder. So I'm explaining why it's colder at the poles. Therefore, areas closer to the equator will be warmer, and the farther from the equator you get, the colder it gets. So that last sentence is the how it affects temperature. So I already explained the why it affects temperature. I explained why it affects the temperature when I talk about direct and indirect light. And I explain how it affects temperature by explaining that close to the equator, it's warm, and farther away, it's cold. So that's covering the how and the why. Things that you need to focus on in this explanation that you make sure you have in your explanation. You need to talk about direct light. You need to talk about indirect light. You need to explain what direct light is. You need to explain what indirect light is, okay? You need to explain that the equator is receiving direct light and therefore it's warmer, and you need to explain that the poles are receiving indirect light and therefore it's colder. Okay, so that's the first model and the first explanation. So now we're going to move on to altitude/elevation. Okay, so I know that this model that you're looking at right now on my screen is probably not the model that you have on your paper. However, I do think that it is the best representation to show how elevation affects temperature, and sorry, not just how, but why it affects the temperature. Okay, so you can do a model that shows just the temperatures decreasing as you get higher. You just need to make sure you use the air molecules in your explanation. So that's why I added it to my model, so that I would be able to use my model to explain the why better. Something that this model could have, what I could have added to this model is I could have added temperatures at each one. So, or even just like ranges of temperatures. So like down here at sea level, I could say like warmest, and then I could say warm here, and then medium here, and then cold here, and then coldest at the top. Or even put numbers here. So like put like 84 at sea level, and then put degrees Fahrenheit. You have to make sure for degrees Fahrenheit. And then put like 72 here degrees, and then so on and so forth up until the coldest. Now in this model, I want you to focus on the fact that I do have a key over here to show that my little circles are air molecules. And then here I'm showing the elevation. So sea level, and then at this line it's 100 meters, at this line it's 200 meters, at this line it's 300 meters, at this line it's 400 meters. So things you need to focus on in this model are, one, the key that I have to show that there are air molecules. And if you count, there are more air molecules in the sea level, and then there's less air molecules as you go up all the way to the top where you only have 2. Now, obviously, this is an exaggeration. There aren't only 2 air molecules up at the top, but this is just a good visual aid to show what is happening to the air molecules as you go up in elevation. The other thing is you do need to show some representation of elevation increasing. Obviously, I know that as you go up a mountain, elevation increases, but remember, when you're drawing a model, it's you proving to me that you understand that as you go up a mountain, elevation increases. Okay, so this is my model. So my explanation using this model is this. So the model above shows that as elevation increases, and then in parentheses, I explain that I'm showing elevation is increasing by the meters on the left-hand side, okay? As elevation increases, the amount of air molecules decreases. And then I explain that that is shown with the circles on the right. So as elevation increases, the amount of little circles decreases. Okay, so that's what my model is showing. So that first sentence is just showing what this model is showing. At sea level, there are more air molecules. So this is still talking about this. So at sea level, there are more air molecules. This causes the air molecules to bump into each other often. The bumping causes friction, which causes heat. Okay, so this is the why elevation affects temperature. There are a lot of air molecules. They're constantly bumping into each other, which is making friction happen, which is making heat. The higher up you go, the more sparse, which just means there's less of them, the air molecules are, which means that there is less bumping, which means there is less friction, which means there is less heat. So those few sentences from at sea level to less heat is explaining the why elevation affects temperature. The last sentence is going to say how it affects temperature. Therefore, the higher the elevation, the colder it gets. Okay, so the why is the scientific reason that temperature changes with elevation. So that's here. That's those sentences right there. The how it affects it is just that the higher up you go, the colder it gets. Okay, now you can rearrange this order. You can say the higher the elevation, the colder it gets early. Like you could say that could even be your opening sentence. That's totally fine. Okay, but you do need to explain about there being less air molecules at the top, and about how when there's less air, there's less friction, and friction is heat. Okay? All right, so those are the first 2. So now we're gonna move on to our number 5. So number 5 is to create a model to show how the closeness to a large body of water affects temperature. So this all has to do with sea breezes. Okay, if you're close to a large body of water, you have sea breezes, and those are going to impact your temperature. So I drew both day and night, and the reason I did that is because my explanation is going to talk about both. So if you are going to, and really you do need to explain both in order to get full credit on this. Okay, so in the day, so first of all, we know that land heats up and cools down faster than water. So the water in this whole situation is going to stay the same temperature. So during the day, the land is really hot. So I have hot land labeled here. The water is cold. So I say cold water here. Now, because the water is cold, it's going to have a high pressure system because cold air is sinking and it's putting that pressure down on the water. Okay. So this is a high pressure situation. There's a lot of air molecules here that are really cold and they don't want to be here. Now, because the land is hot, that hot air, the air right above it, and then that hot air rises, creating a low pressure system. So because there's a low pressure system here, oh, I didn't label that. You should definitely label that as an L, okay? So because there's a low pressure system here, Pressure systems always move from high to low. So you're going to get a breeze from that cool sea air going over the land. And that's going to cool off the land considerably. Okay. And then that hot air up here is going over to the sea and then cooling and sinking. So that's during the day. At night, it reverses because the land cools down super fast. As soon as the sun is gone, the land cools down. And that's going to create that high pressure system. Now remember, these are like mini pressure systems. They are not like pressure systems that are happening across the whole United States that cause storms and stuff. These are just little mini ones that cause breezes instead of like strong winds. So here we have a high pressure system because that cold air is sinking because the land is so much colder, okay? So this high pressure system is now on the land. Well, the water's temperature didn't change when the sun went away. The water's temperature stayed the same. So as that warm water is happening, it's creating a low pressure system because it's going to move that air. So the air above it is cold, so the warm water is going to warm it, and then the air is going to rise up, causing a low pressure system. And then we know pressure systems move from high to low, so it causes a cool, what's called a land breeze, where the breeze is going from the land to the water. But here is actually the more important part. Up at the top, that warm air that rose up from the ocean, or sorry, from the large body of water, is now going to move over to the land, which is going to actually keep the land a little bit warmer. And I actually go through that in what I just said in detail with this explanation. So let's go through the explanation. Oh, and this is number 6. I just had to glue over this when I was doing this. So this is number 6 right here. So the explanation. The model above shows how the heating and cooling of land, so land heats and cools, and the water's temperature remaining the same. So throughout the day and night, the land heats and cools, but the temperature of the water remains the same. Land and sea breeze, this situation creates land and sea breezes that keep the land's temperature more mild. Okay, so this more mild that I say here is one of the how this affects temperature, okay? So during the day, the water is cooler than the land, which creates a high pressure system over the water and a low pressure system over the land. So that's all I just explained up here. Pressure systems move from high to low, so a cool breeze from the ocean cools off the temperature of the land. So the cool breeze from the ocean cools the temperature of the land over here. However, during colder months and or the night, okay, the water is warmer and the land is colder. So the reason I specify during colder months is because if you are a place that is near the ocean and you are getting your water from the equator, okay? So let's say you are France, okay? And you're getting your water, your current is coming from the Gulf Stream, okay? Well, in December, when it's really, really cold on the land, the water is going to be very warm. So that's going to prevent really snow from happening. It's going to keep France a lot warmer because the water is so warm. So it's not just at night, it's also those colder months, okay? The water is warmer and the land is cooler. So this reverses the process, which causes a cool breeze to go towards the ocean and warm air from above the ocean to move toward the land, which is going to keep the land a little bit warmer than it otherwise would be, okay? And then I give you, so that's all the why the sea breezes affect, or the closeness to water affects temperature, and then here's the how. Therefore, land that is closer to a large body of water will have milder temperatures, okay? So there I'm explaining the why, talking about the sea breezes, and then the how, explaining that any city or land or state that's close to a large body of water is going to have temperatures that are a little bit more mild. Okay, so now we're going to move on to our last model. So this model is probably the hardest, and there's also a lot of different things you could do. So I chose to do ocean currents because that's the one that makes the most sense to my brain. But you could also, in this situation, you could do the Hadley cell, Ferrel cell, and polar cell, and you could show the wind convection currents that are occurring. So you would just draw the Earth and you would draw the different latitudes of the Earth and you would draw those cells, those convection cells that we did in the global convection currents activity. Okay. So I chose the ocean currents. Something that this model is missing is it should have this current right here labeled as the Gulf Stream and this current right here labeled as the California current. Because if I need to explain specific countries, I want to make sure that I'm discussing the current that is going to those countries. And those are the only two that we've really focused on. So those are the only two that I would really expect you to know on the test, okay? So this is just showing that at the equator we have, or in the Northern Hemisphere, we have our clockwise currents that are coming from the equator going up and then cooling at the poles and then coming down. Okay, so in this model, I'm showing that Mexico and California are getting their water coming down from the poles, whereas Northern Africa and Europe are getting, or sorry, Europe and the east coast of the United States are getting their currents from the Gulf Stream, from the equator, and then Northern Africa is actually getting cold water coming down from the poles. Okay, so here's my explanation. The model above shows how two major ocean currents move on Earth. So I didn't put all of the ocean currents because that would just be ridiculous. Oh, and see here, I mentioned a state and a country, and I didn't put the labels up here. So you would need to make sure that you labeled this up here, okay? I'm going to focus on California and Europe. So California's over here, Europe's over here. I know my drawing's terrible. On the west coast of the United States, the ocean current is bringing cold water from the poles. So that's talking about right up here. This is because the Coriolis effect causes water to bend to the right in the northern hemisphere. Okay, that is very important. The reason that California is getting cold water is because of the Coriolis effect. So if you're going to talk about California or you're going to talk about Europe, you need to mention the Coriolis effect. The cold water from the poles keeps California's coast colder than it otherwise would be. Okay, so this is kind of referencing those the sea breezes from up here, but all that you're really talking about is that California's water is colder. Okay, and that's all you really need to mention. In Europe, the Gulf Stream, and see, I should have labeled the Gulf Stream here, is bringing warm water from the equator up to Europe, because it's still in the northern hemisphere. So it's still in the northern hemisphere. So it's the Coriolis effect is still turning it clockwise. Okay. This causes Europe to be warmer than it otherwise would be. So if you look at Europe, Europe is actually closer in latitude to like Canada and like the northern part of the United States. And they have very similar weather to California. Okay. And then I explained the how. So therefore, ocean surface currents affect temperature by bringing warm water from the equator up to polar areas and colder water from the poles down to areas near the equator. And this is going to keep it more mild. This is what we talked about on Monday. So if you did the atmospheric circulation things, it would be very similar. The how would be very similar. You would talk about how air from the equator is being pulled up to the northern parts and the southern parts, and air from the poles is being brought down to the equator to keep the equator a little bit cooler. This is in the Edpuzzle that we did about convection currents. This talks about that. Your model would be different. So when you're explaining your model, you would have to talk about how the Hadley cells bring warm air from the equator up to the Tropic of Capricorn, the Tropic of Cancer, and you would have to talk about how the polar cell brings cooler air down to the tropics, and so on and so forth. But the how would be very similar. It would just, instead of saying ocean surface currents, you would say the global convection currents. Okay, and then instead of saying water, you would say air. Okay, so these are this is the key to the performance tasks study guide. I'm also going to post this on Google Classroom, so you don't have to like watch the video and pause and read things. So this will also be on Google Classroom as well. But this was my explanation so that you understand why I did this, if there are other models, what you could do, and I hope that this helps. If you are confused about anything, please email me or send me a Jupyter message. I will have my phone on me today so that I will be able to get back to you guys as quickly as possible. Thank you very much.